Greetings and welcome to Precalculus. We're going to talk about polynomials and rational functions, specifically quadratic functions. Okay, let's jump in and start talking about what a quadratic function looks like. We're going to say f of x equals ax squared plus bx plus c, where a, b, and c are real numbers, and very importantly, a does not equal 0. If a equals 0, then the x squared term drops out, and that's a linear function. And this is supposed to be a quadratic, so we need the x squared to exist, so a cannot be 0. Now, if we get rid of all the extra stuff, we can see that we do have a function, let's call it s of x, equals x squared. This graph is of the graph of a parabola, so any quadratic function is also a graph of a parabola. We can get a lot of information when we have our function in this standard form. First of all, a can be greater than 0 or a could be less than 0. If a is greater than 0, then our parabola opens upward. If a is less than 0, then it opens downward. We also know that if our absolute value of a is anywhere between 0 and 1, it stretches away from the y-axis. We learned that in chapter 2. And if the absolute value of our a is greater than 1, it compresses towards the y-axis. It grows faster, so it compresses towards the y-axis. Now let's take a look at a few examples. We're going to take a as 2 and negative 2. A will be 1 and negative 1, and a will also be 1/2 and negative 1/2. And here are the graphs that come about. I'm going to graph the positive values on the left and the negative values on the right. Okay. When a is positive, it better open up, hence doing it all on one graph. All right, here we go. When a equals 2, it's compressed more towards the y, versus a equals 1. Here's the normal parabola in red. In blue, since a is greater than 1, it compresses towards y. Since a is a fraction, it's going to go away from it stretches away from the y-axis. But all of these, since a is positive, opens upward. Now looking at a equals negative 2, a equals 1, negative 1, and a equals negative 1/2. Again, a equals negative 2. It still compresses towards the y-axis, but it's pointing down because it's negative. A equals negative 1, regular parabola, but opens down because a is negative. And a equals negative 1/2. It stretches away from the y because it's less than 1. But again, opens downward because it is negative. Now this standard form of the quadratic equation, f of x equals ax squared plus bx plus c, we can get a lot of information. It's actually the squaring function. Part of it is the squaring function. And we can also write it as this horizontal shift where x minus h is our horizontal shift all squared. When it's minus h, it's a shift to the right. When it's plus h, it's a shift to the left. Okay, so when this says x minus h, it's a shift to the right. When it says x plus h, it's a shift to the left. Taking it one step further, we can also do a vertical stretch. That's this a value. And from this a value, we're either going to stretch away from the y or compress towards the y, depending on what our value of a is. And finally, we have this plus k is a vertical shift. When k is positive, a plus k, we shift it up. If it's a minus k, we shift down. So we can actually look at this standard form of the equation where f of x equals ax squared plus bx plus c. We have a secondary form where we can have a times the quantity x minus h all squared plus k. All right, here is our standard form, our second standard form, and it is f of x equals a times the quantity x minus h all squared plus k. And again, a cannot be 0. If we do, we get rid of this quadratic term and it's no longer a quadratic equation or a quadratic function. Now, there's a lot that this version of our standard form tells us. First of all, it tells us if it's opening up or down, depending on our value of a. If a is negative, it opens down. If a is positive, it opens up. It also tells us where our vertex is. Our vertex is at hk, the actual numerical value of h. So when it's minus h, it's h. If this says plus h, it's negative h. K. Okay. So here we go. If a is greater than 0, it opens upward, and our hk, our vertex, is actually a minimum of f. If a is less than 0, meaning it's a negative number, it opens downward with a vertex at hk, and this is a maximum of f. So just having it in this format, it tells us a lot of information. Our axis of symmetry is when x equals h. That's our axis of symmetry. Because remember, parabolas are mirror image from this axis of symmetry. You fold it in half and it looks exactly the same on one side as it does the other. So let's look at an example. Writing our equation of a quadratic function. So we want to find the standard form of a quadratic function, f, whose graph has a vertex of negative 3, 4, and passes through a point, negative 4, 7. Does f have a minimum or a maximum? We know with a parabola, we do have a minimum or a maximum, but we just don't know, is this vertex a minimum or maximum? So we're going to figure this out. Here we go. Let's take our standard form where our vertex is hk. Now remember, we're given our vertex of negative 3, 4. So let's go ahead and plug that portion into our equation. So if our vertex is negative 3, 4, h equals negative 3, and k equals 4. Plugging that in to our standard form, we get f of x equals a times the quantity x minus negative 3. Remember, the value of h is negative 3, all squared plus k, which is 4. Doing some math here, we get a times the quantity x plus 3, all squared, plus 4. Now let's go ahead and change just the way we write things. Instead of using f of x, let's use a y and rewrite it as in y equals a times x plus 3 all squared plus 4. Now we can plug in that point we're given and given an x value and a y value, and then we're going to find our a value by doing this. So plugging in a 7 for y and a negative 4 for x, we get 7 equals a times negative 1 squared plus 4. Well, negative 1 times negative 1 is 1. A times 1 is a. Let's subtract 4 from both sides, and we get a must equal 3. Now, given a equals 3, and we know our vertex, we can rewrite our standard form using what we know about a, what we know about h, and what we know about k. Throwing all of that in there, we get f of x equals 3 times x plus 3 squared plus 4. And because our a value is greater than 0, we know that our vertex is a minimum. It opens upward. So our vertex is at the minimum portion of our parabola. Let's run through an example with all the steps that we're going to need to figure out a standard form for our quadratic function. So first, we want to identify our a, our h, and our k. So for example, let's say f of x equals negative 3 times x plus 2 squared plus 12. Now we have to remember that this in standard form is x minus a value. So this is really going to be negative 3 times x minus a negative 2, because a minus negative is a positive, all squared plus 12. So now we can figure out our a value is negative 3, our h value is negative 2, and our k value is 12. Next step. Let's determine how the parabola opens. All right. Well, that has to do with our a value. A is negative 3, so this means it's less than 0. It opens down. Let's find our vertex. Our vertex is hk. Well, our h value is negative 2 and our k value is 12, so our vertex is negative 2, 12. So far, it's not too terrible. Step 4, let's find the intercepts for our x-intercepts. Now, our x-intercept is when y equals 0. So we're going to set this whole entire function, our f of x, to 0. And by doing that, we're now going to solve for our x values. So I'm going to go ahead and subtract 12 from both sides, and I get negative 12 equals negative 3x plus 2 all squared. I am going to divide by negative 3 to both sides, and we get 4 equals x plus 2 all squared. I'm going to go ahead and take the square root of both sides, and I have to remember that on the left now because my squaring's on the right. I have to do the plus and minus. So plus and minus square root of 4 equals the square root of x plus 2 all squared. The square root and the square cancels out, and the square root of 4 is 2. So I get plus or minus 2 equals x plus 2. I'm going to break this apart. So where it says x plus 2 equals 2 and x plus 2 equals negative 2. And I'm going to solve these individual equations. So I'll let you run through that. But I get x equals 0 and x equals negative 4. So my intercepts, I did all that work to find my intercepts. My x-intercepts are 0, 0, and negative 4, 0. Remember, I set y to 0, so y is in the second position. The next step, we've got to find the y-intercept if one exists. So the y-intercept is when x equals 0. Right? So let's throw a 0 in. So I want to know what the function is at 0. Throw a 0 in there. And if I solve this, you will see that my y-intercept is 0, 0. I'll let you work through all the little steps there. But my y-intercept is 0, 0. All right, we're getting there. We just have another step to go. We're going to actually sketch the graph. All right, here's all the information that we gathered from the previous 5 steps. We know our vertex is negative 2, 12. We know that our x-intercepts are negative 4 and 0 and 0, 0. Our y-intercept is 0, 0. Our line of symmetry is negative 2, and there's one more thing we know. Since A equaled negative 3, we know this opens down. Okay, so our vertex, if this opens down, this means our vertex is a maximum. So I'm going to plot these points that we know we have. We have negative 2 and 12. We have negative 4 and 0. We have 0, 0. And we know this is a maximum. Here's our line of symmetry. So there's going to be a mirror image on this, on each side of this line. Now I'm going to try and do my best to connect the dots as a parabola would. And there we go. This is our maximum. It opens downward, and I've connected the dots. Okay, now if you would have tried to connect these having it upward, there would have been an issue. You couldn't necessarily connect these two dots and this one by going upward. You'd kind of have to come back at each other, and that's not what this function's all about. This function Quadratic functions are shape of a parabola. All right, let's talk about graphing a quadratic function like f of x equals a squared plus b squared, or ax squared plus bx plus c. Now, because these two ways of writing a quadratic function are equivalent to one another, I actually find getting it into this standard format of a times x minus h all squared plus k is a lot easier to graph our quadratic function. So if we can change this ax squared plus bx plus c into our other standard form, that's a good thing for us when it comes to graphing. So let's go ahead and take an example of f of x equals x squared plus 4x plus 3 in this standard form. And let's change it over just by doing a few little steps, get it into where we can find our vertex very easily and figure out if it's opening up or down. First things first, we are going to use completing the square to find, because we want something to be squared, we're actually going to complete the square and force it to be in this format. All right, I'm going to take the middle value, -4, and I'm going to do a little process to it. First of all, I'm going to take -4, divide by 2, and I get -2. I'm going to take this -2 and I'm going to square it and I get the value 4. This 4 is what I'm going to add to the first two terms to force it to be a perfect square. But I can't just willy-nilly add 4 to equation. So I'm also going to subtract 4 at the same time. So I'm going to add 4 and subtract 4 at the same time. All right, so we get x squared minus 4x plus 4. Here's where I'm adding 4. But then on the same side, I'm going to subtract 4 because then I really didn't add anything. 4 minus 4 is 0, and I haven't manipulated the function in any wrong way in math, any illegal way in math. So then I have on the outside of these parentheses, I've grouped the first thing because this is going to be a perfect square. So I have 3 minus 4. Well, this factors into x minus 2 all squared plus 1. So here is our function of f of x equals x squared plus 4x plus 3 in our secondary standard form, which is x minus 2 all squared minus 1. And from here, I can see my a value is 1, so this opens upward, and my vertex is 2, -1. So I can get a lot of information just from how this is written in this format. Let's take another example. Right? So we have g of x, 5x squared minus 20x plus 8. Now this one's a little bit more tricky because I do have a value in front of my x squareds. So I think the first thing I want to do is actually group the first two terms, because that's ultimately what I'm going to use for completing the square. And I'll factor out this 5 in front. So if I factor out 5 out of this blob, I get 5 times x squared minus 4x. Now I haven't done anything with this plus 8. I'm just carrying it along for the ride. Now I'm going to finagle this parenthesis stuff into a perfect square. But I need to be very careful because I can't forget there is a 5 out here. All right, so taking this middle term, I'm going to cut it in half. I get -2. I'm going to square it, and I get 4. So to complete the square for the parenthesis, it's going to be plus 4. But remember, there is a 5 out here. So if I bring 5 times 4, that's really 20. So I can't just subtract 4 on the outside. I actually have to say -4 times 5. That will give me my -20. So 5 times 4 is 20. Minus 20 is the 0 I need to not break any rules in math. All right. So this first blob will factor into x minus 2 all squared. So I have 5 times x minus 2 squared plus 8 minus 20. But plus 8 minus 20 is minus 12. Oh my goodness, minus 12. Again, this format tells us a lot of things. First of all, our value of a is 5, meaning it does compress towards the y-axis because it's greater than 1. It's positive, so it's upward. My h is 2, and my k is negative 12. So this tells me a lot of information just by how it's in this format. All right, if you are one for formulas to use to be able to quickly convert one function type to another, so one form to another, this few minutes of discussion is going to be right up your alley. All right. So given our standard form of ax squared plus bx plus c, I want to get it into this format without having any numbers. And think about that steps that we did in the previous example. There were specific steps that we did to complete the square, to get it written in a squared format and with our h and our k. So here we go. First things first, we're going to, out of the first two terms, we're going to factor out the a. If we factor out the a, we're left with x squared plus bx over a, because remember, I've divided out this a. Next step, I've got to complete the square. I take half of the ba, which is b over 2a, and I square it, and I get plus b squared over a 4a squared. But once I add it, I also have to subtract it. So this is going to be b squared over 4a squared. So that equals my 0. This is the completing the square part. But I don't need this part in my parenthesis. So I'm going to multiply the a back in and get rid of this part and bring it onto the outside. So doing that, I now have a times x squared plus b over ax plus b squared over 4a squared minus the a times b squared all over 4a squared plus c. Now you might see that you can reduce this. I've got an a on top and I've got an a on the bottom, and I can completely reduce this a little bit, and this portion is going to be a perfect square. So my perfect square is b over 2a. It's this thing cut in half. So just put a 2 down there and you get b over 2a, all squared, plus c minus b squared all over 4a. Remember the a's canceled out here, but I still have a b squared there. Now look at what this is going for now. This tells us to find h, that's going to be negative b over 2a. K is c minus b squared over 4a. So given values for a, b, c, I can figure out h very quickly, and I can figure out k very quickly. Just plug them in, and you can get it into this format fairly quickly. So let's find the vertex of this value. Well, we know the vertex is hk, and we're going to find the x-coordinate by use of h equals negative b over 2a. This is of the vertex, h, remember? And our k value is our function at that value, because sometimes we're not given this c value, but we could find out our y-coordinate by plugging in our h value, and we would calculate k. Now, if we do have a, b, c, we can actually use the a, the b, and the c in the function up here for k to find k. But there's a couple ways of doing it. Now remember, if a is greater than 0, then k is actually the minimum value of f. If a is less than 0, a negative number, then k is the maximum value of our function. Okay. So there's a lot we can do with just manipulating this function. It's kind of pretty cool, actually. All right, let's run through the steps that it's going to take to graph a quadratic function. So we have our function. It is in the form of ax squared plus bx plus c. So our function, f of x, is 2x squared plus 8x minus 10. First of all, let's identify a, b, and c. A is 2, b is 8, and c is negative 10. Second step, does it open up or down? A is 2, which means it's greater than 0, this opens up. Let's find the vertex. Now we get to use those formulas to find the vertex. All right, h, our vertex, is negative b over 2a. Well, b is 8, so negative 8 over 2 times 2. 2 times 2 is 4, so negative 8 divided by 4 is negative 2. Now we could use that function of k equals c minus some b stuff, but we could also just evaluate the function at this negative 2. So that's the way I'm going to go about doing it. K is when I evaluate it at the h value, which is negative 2. So 2 times negative 2 squared plus 8 times negative 2 minus 10. Negative 2 squared is 4. 2 times 4 is 8. 8 times negative 2 is negative 16 minus 10. 8 minus 16 is negative 8, and negative 8 minus 10 is negative 18. Knowing that it opens up, this k value is a minimum at negative 18. So our vertex is negative 2, negative 18. All right. Let's find next stuff. We're going to have to find the x-intercepts. The x-intercept is when our f of x equals 0. So let's go ahead and set our function to 0. And we're going to solve this for our x. Now I find that it's actually easier to divide everything by 2 so we can get rid of this 2 out front. Once we do that, we get 0 equals x squared plus 4x minus 5. And this is factorable. So let's go ahead and factor it. It's x plus 5, x minus 1. And therefore we get x either equals negative 5 or x equals 1. And so our intercepts are negative 5, 0, and 1, 0. Step 5. Let's find our y-intercept. Our y-intercept is when our x value equals 0. So let's just plug in 0 and see what we get. So f of 0, 2 times 0 squared plus 8 times 0 minus 10. Well, 0 times anything is going to be 0, and 0 times 8 is 0. So we get negative 10. 0 plus 0 minus 10 is negative 10. Okay, we have a lot of information, so let's go ahead and graph this guy. All right, we also know our symmetry because we're symmetric around x equals h, and our h value is negative 2. So let me just put a line right at negative 2 right now. So there's my line of symmetry. And I'm going to plug in everything we know. First of all, we know this opens up. We know our vertex is negative 2, negative 18. So negative 2, negative 18. We also have our y-intercepts at negative 5, 0. So negative 5, 0. And 1, 0. We also know that it crosses the y at 0, negative 10. So way down here. And because it's symmetric around this line, if I have a point 2 away from the line at negative 10 on the right, I also have a point negative 2 to the left. This is symmetric. This is where the symmetry comes through. So without even doing any math, I know this is 0, negative 10, and this one is negative 2, negative 10. Okay, so I found another point just by using the symmetry. Now I'm going to carefully connect those points as best as I can in the shape of a parabola. And there's our parabola. Not bad, right? Knowing which way it opens up, it speeds us up. Also, finding the vertex speeds us up because we know that is a point, because it opens up, we know this is the minimum point. It has to go up on each side of this point. All right, now let's take a look at a quadratic function. We're going to still graph our quadratic function, and we're going to solve the related inequality that goes along with it. So we're going to first graph the sketch. It's very similar to what we just did, but this is negative 2x squared plus 8x minus 5. Before we had a minus 10. So we are going to have to go through all the steps to graph this function. And then we're going to determine the domain and range of our function and also solve the inequality where it's greater than 0. Okay, so our function is greater than 0. We're going to solve that inequality by actually graphing and looking at our graph. All right, so let's take a peek at our solution. F of x equals negative 2x squared plus 8x minus 5. So first of all, I'm going to recognize what a, b, and c are. So a is negative 2, b is 8, and c is negative 5. I am going to find h and k using our formulas. So h is going to be negative b over 2a, negative 8 over 2 times negative 2. That's negative 8 over negative 4, which is 2. Our k value is going to be our function evaluated at 2. That I feel is easier to remember versus the actual formula for k, but you can use it if you want. All right, throwing in a 2, we're going to get negative 2 times 2 squared plus 8 times 2 minus 5. That's going to be negative 2 times 4, negative 8 plus 16 minus 5 is going to be 3. So our vertex is at 2, 3. Okay, so here's our new function written in the new format. Negative 2 times x minus 2 all squared plus 3. How did I get that? I put my h in where h goes, my 3 goes in where my k went, and this is my a value, which is just our coefficient of our x. All right, okay. Our intercepts is when our f of x equals 0. So I am going to set it to 0, and I'm going to solve this equation. Let's subtract 3 from both sides. Then we get negative 3 equals negative 2 times x minus 2 all squared. I'm going to get rid of this negative 2 by dividing both sides by negative 2. And I get 3 halves equals x minus 2 all squared. I'm going to take the square root of both sides, remembering that our side without the x needs the plus and minus. So I get the square root of 3 halves equals x plus 2, x minus 2. I'm going to add 2 to both sides, and I get my x value equals 2 plus or minus the square root of 3 halves. Now I threw this in the calculator, and I got about an x value of 0.78 and 3.22. That was throwing it into the calculator. All right, so I do know my x-intercepts. My next step is to find my y-intercepts. That's when our x value equals 0. So in my function, I'm going to throw in a 0, and I'm going to see what's going to happen. Okay, 0 minus 2 is negative 2. Negative 2 squared is 4. Negative 2 times 4 is negative 8. And negative 8 plus 3 is negative 5. So my y-intercept is at 0, negative 5. Okay. Now, my line of symmetry is when x equals 2. Why 2? Because that's my h value. Here we go. I know my f of x equals negative 2x squared plus 8x minus 5 must be greater than 0. That's what I'm trying to figure out. Now here's my graph. I've used my x-intercepts, my y-intercept, my line of symmetry, and my vertex. Now, I'm really looking to see where is this function above the x-axis. When it is above the x-axis, it is positive. And therefore, in this region, it is positive. In this region, it's negative. And therefore, the values that are above the line are from this point to this point. Meaning, my x value, when x, okay, use a different color here. This inequality is true when 0.7753 is less than or equal to x is less than or equal to 3.2247. So it's in between these points that it crossed all my x. So I know those by my x-intercept values. Okay? Everything in this region was above the x-axis, and therefore it's positive. If this value asked me for less than 0, then it was everything over here, and over here is negative on my function, but in here it's positive. Okay. Here, all of the values for x were under the x-axis, right? Here are my values of x. Anything here made my function be negative. Any values on x that are to the left of that point was also negative. And it's only these values in between my two x values made it positive. Okay, I hope that kind of makes sense. If I was looking for negative, I would do any of my x values less than this point and greater than that point, but I wanted where it was positive, so it's in between those 2 points and including those 2 points. All right, so here's where we come to an actual application of what we're doing. And a lot of the times I hear from math students, well, why do I have to learn this? It's all x's and y's, and we never use x's and y's. Well, there are actually applications of this math that we're doing. So let's take a look at one. We're going to track a moving object. Now, here we go. Lots of information to throw at you right at the start. Number 1, the height, h, in feet of a ball thrown upward at initial velocity of v sub 0, or v0. Feet per second from the point of h0, feet above the ground, is going to be this function. H of t equals -1/2 the gravity of Earth times the time squared plus the velocity, the initial velocity, times t, plus the initial height. Okay, t is the time in seconds after you throw the ball. Now, gravity is pretty standard. Gravity doesn't change for most math equations. We're going to use 32 feet per second squared. So we can replace this g of e, which is our gravity of Earth, by 32. So let's go ahead and start throwing in some information. Let's say we threw the ball upward from a cliff and we are 50 feet high from ground on this edge of the cliff. The maximum height that it was reached, this ball, was 99 feet. We're going to find the height of the ball as the function of time. We're also going to figure out how long did it take the ball to reach this highest point. Now, this highest point, if you can imagine throwing a ball, it's going to be in a parabolic shape. The ball kind of goes up and then it reaches a height and then it comes down. And it turns out our highest point is 99 feet. And we want to know the x value that goes around our time that it took to reach that maximum height. All right, let's talk about this solution. We are given the initial equation of the height at any given time will be -1 height, gravity of Earth, times the time squared, plus the initial velocity times time, plus the initial height. We know our gravity of Earth is 32 feet per second squared. We know our initial height of the cliff is 50 feet. So let's go ahead and throw those in and see what we can get. We can reduce this a little bit. Okay. So -1/2 times 32 is -16. So our equation that we're going to use, our height in terms of the function of time, is going to be h of t equals -16t squared plus our initial velocity times t plus 50. As much as it looks a little confusing, we actually have a quadratic function, and I'm going to pull out the a, b, and c values. A was -16. B is our initial velocity, so v of naught, or v0, and our c is 50. Since A is negative, it opens down. Well, that's expected. You can imagine throwing a ball and it is in a parabolic shape that first goes higher and then comes down. I'm sure you've seen a lot of baseball games, or you yourself have thrown a ball and you know it goes up and then goes down. At least if you're not throwing it like, a professional pitcher, which still it does curve down. It just doesn't look like it. It looks like it's thrown straight. Our vertex is a maximum. And we know that part of our maximum is the height at 99 feet. All right, our vertex is going to be negative b over 2a, and our k we know is at 99 feet. That's our vertex, our maximum feet. Okay, so I need to figure out this time. That is actually our vertex time. So our time is going to be our b value, which is negative our initial velocity, over 2 times negative 16. Well, a negative over a negative is a positive, so our t value is actually our initial velocity over 32. Now I know it looks like, oh, well, we can't solve this because we don't know what our initial velocity is, but hang in there. We know that if we evaluate our function using this value, we will get 99. Okay, so if we evaluate it at h, we get k. So let's go ahead and throw in our function at our value of velocity, our initial velocity over 32 equals 99. Okay, here we go. 99 equals, well, negative 16 times our initial velocity over 32 squared plus our initial velocity times our initial velocity over 32 plus 50. That's just plugging in for our quote-unquote t value. Doing some math here, this is our initial velocity times initial velocity is initial velocity squared. We do get, and your book does it a little different, I'm actually multiplying it out, so 32 times 32 is 1024. I am going to make common denominators so I can combine these two values. So I need to multiply both top and bottom by 32 for our second term. And we get negative 16, our initial velocity squared, all over 1024, plus 32 initial velocity squared, all over 1024. I'm going to subtract 50 from both sides, getting our variable all in one spot and combining our variable. Negative 16, but plus the 32 is a positive 16, velocity squared all over 1024, equals 49, because 99 minus 50 was 49. I'm going to get rid of my denominator by multiplying the 1024 to both sides. Okay, we're getting there. Just hang in there. I get 50, 176 equals 16 times our velocity squared. I'm going to divide by 16 to both sides. I get 3,136 equals our velocity squared. I'm going to take the square root of both sides. Now keep in mind our velocity cannot be negative. Our velocity is always positive. And therefore I don't care about the negative version. I just care about the positive version because our velocity is always over 0. And we get 56. Is our velocity. All right, so now that I actually have an actual value for v of 0, I'm going to plug it in here and see what our time is. So 56 divided by 32 will get us our time. And our time ends up being 1.75 seconds. So after we throw the ball at initial velocity of 56, I think we are feet per second. Yes, feet per second. In 1.75 seconds, the ball reaches its highest height at 99 feet, and then it starts coming back down. And unless there's another cliff on the other side where we're throwing it to, it will eventually hit the ground, which is all the way down to the ground, 50 more feet than where it started out as. Well, it doesn't hurt to go through one more example. Let's find our maximum area A farmer wants to build a rectangular grazing pen using a straight stone wall for one side, and he has 100 feet of fencing for the other 3 sides. What is the maximum area that can be enclosed? What are the dimensions of the pen? Now you might be asking, well, how is this ever related to a parabola considering that this is a rectangle? Well, the parabola is actually going to be plotting the area depending on the dimensions of the pen. So let's take a look at this. I want to sketch out what this really means. Okay, so I have this rectangular pen, and on one side is a stone wall, and the other 3 sides are going to be the fence. Now I know I'm going to let my length be an x and my width be a y and my other length be an x as well, because I know for a rectangle the 2 opposite sides have to equal one another. I also know my area of a regular rectangle is going to be length times width, but since I'm using x's and y's, I'm going to go ahead and use x and y. I also know the 3 sides of the fence that is actually built with fencing material, x plus y plus x, in other words 2x plus y, equals the 100 feet of fencing that I have. Okay. Now, I want this all in terms of x. I don't want any y's when it comes down to it. I just want one unknown. So using this second equation of 2x plus y equals 100, I'm going to solve that for y. And I get y equals 100 minus 2x. So inside my area formula, I'm actually going to replace this y with the 100 minus 2x, and I have only x's left. In fact, my area is 100x minus 2x squared. And if I just change that around, you will see that this area formula is actually a parabola, a parabolic, a quadratic function, the shape of a parabola. Our maximum value is going to be the vertex of this parabola. So I've just got to figure out what is my vertex. Okay, so rewriting this function to where it looks more like our normal quadratic equation, I get negative 2x squared plus 100x. Okay, a is negative 2, b is 100, and c is 0. Let's plug in for h, which we have our formula of negative b over 2a. b is 100, so we have negative 100 over 2 times negative 2. Negative over negative is positive. 100 divided by 4 is 25. Using our 25 to plug into our equation, we're going to find our k value. Plugging that in, we get negative 2 times 25 squared plus 100 times 25. 25 squared is 625. And if you throw that into a calculator, you get 1250. And therefore, our maximum that we can have is 1,250 feet. That's our maximum value for a of x. Now, our dimensions, we still want to figure out. Throwing our 25, our h value, into our equation, we know that x equals 25. Throwing our x in there, and for our y value, remember we had this second equation for our y value, right there. 2 times 25 is 50. 100 minus 50 is 50. So the dimension of the largest area we can create will be 25 by 50. And that is with 1 stone wall and 3 other walls using our fencing material. So our x is 25, these 2 sides are 25, and these 2 sides are 50. So one of our stone walls is 50 feet, our fence wall is 50 feet, 25 feet, and 25 feet. So 25 plus 50 plus 25, of course, is 100. So we've used up all our materials and we made the largest pin size that we possibly could. 25 by 50. With a square area, maximum area of 1,250 feet squared. All right, let's sum this chapter up. Our quadratic function is f of x equals ax squared plus bx plus c, where a does not equal 0, can also be written as f of x equals a times h minus x. Oops, my bad. Uh-oh, there it is. That should have a square on it right there. So a times x minus h all squared plus k. We also know the vertex is at hk, where h is negative b over 2a, and k is our function evaluated at h. I find that's the easiest to go versus that other formula. A vertical line, h equals our h value is our axis of symmetry. Our graph opens up if our a value is greater than 0. It opens down if our a is less than 0. Our graph is wider than our standard parabola if the absolute value of a is less than 1, and it is narrower if our absolute value of a is greater than 1. Our y-intercept is actually at c. So looking back at the other form, this ax squared plus bx plus c, our y-intercept is at c. Our x-intercepts, well, we've got 3 different versions of knowing if we have x-intercepts. The first is if our b squared plus 4ac is greater than 0, then our actual x-intercepts we can find using the quadratic equation. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. If our b squared plus 4ac actually equals 0, then our x value is going to be negative b over 2a. In other words, our h value. And if our b squared minus 4ac is less than 0, then there's actually no intercepts, because we're not allowed to take the square root of a negative number in the real numbers, and therefore there are no intercepts. So that's it for this video. I know that was quite a lot of information. Good news is you can always rewind, rewatch, slow me down if need be. And if you have any questions, reach out to me. That's it for this video. Until next time, be seeing you.